and thank you all for coming. Today, like I said, I'm going to talk about Graceful Shutdown with Structured Concurrency. And I work for 47 Degrees, soon to be Xebia Functional. So as the company name implies, I want to talk about Graceful Shutdown in terms of functional programming. So some of our goals with functional programming is to make things type safe, checked by the compiler. So today we're going to see a little bit about how we can do that. But before I start, let me briefly announce myself. So I'm Simon. You might know me from my work on GitHub, mostly on the Arrow project. You can also find my LinkedIn and my Mastodon accounts. I'm no longer promoting my Twitter for obvious reasons. So what do I want to talk about today? Well, first of all, I want to clearly explain what is a problem statement, and I'm going to be talking about this in the domain of microservices, distributed systems. But the problem of Graceful Shutdown can appear in much more places like that. Also, CLI applications might sometimes need to gracefully shut down. But today, I'm going to talk about server-side things. I'm going to cover also what are resources. I'm going to do a small recap of what is structured concurrency and how does it relate to resource management. And then we're going to implement a small real-world example about how we can apply these things in a microservice environment. So what are resources? So most of us have to deal with the resources pretty much every day. So if we're building a server or a front-end application or any kind of applications, we very often have to talk about with a database. We typically do this with a data source, or we have to work with files or with sockets or things like that. These are things that are very important that we gracefully close them. For example, the operating system has a limited amount of file handles. If you don't properly close them, eventually the operating system will run out of file handles and we'll see performance degrade. So it's very important that we close them and we work with these delicate things. It's very important so that our systems can keep working very efficiently. So when we are working with microservices or distributed systems, we often have to deal with scaling. So for example, in the morning, people start waking up, so we might need 2 pods or 2 servers to handle all the incoming traffic, and then people go to work, so people are not supposed to be on their personal websites and their personal things, so traffic dies, so we can close some servers, and then people get off work and traffic booms again because everybody is going on their facial social networks or buying stuff online, doing all these kind of things. So we need to scale up our system to be able to handle this traffic. And when people are going to sleep later in the day, traffic dies, so we can start cleaning up our resources, our machines again. And we want to do this because, we have an energy crisis, so we want to save energy. We don't want to waste energy. We don't want to waste resources. Also, we want to keep our bills as low as possible because we don't like to pay for things that we're not needing or using. And so over the day, demand changes very quickly in our field, in our domain, so we need to be able to handle these things very, very quickly throughout the day. So as you can see, it's important that we can start and close servers as needed, and we need to do so in a graceful way. And similarly, another use case can be staged rollouts. So typically, we want to do continuous development. So imagine that we have clients communicating to our system, and we have 2 servers running on version 1.0, and we need to roll out a new version. We roll out version 1.1 alongside version 1.0 because we don't want to bring our system down to roll out this new version. And when everything goes well, we roll out the other 1.1 service, or we go back to the 1.0 service. So again, this is a use case of why we need to start and close servers, and everything needs to be working efficiently. So we want to be able to reason about resource safety in a strong and type-safe manner. That should not be there. So let's take a small example. I have here a simple stub server, and it implements the auto-closable interface. So it prints, I'm starting the server when you create this class, and it has a function to handle the routes. And it has a close method that says, okay, whenever you call this close method from the auto-closable interface or the closable interface, it's going to close the server. So it's going to unbind the ports that it bound to from the operating system, freeing up these resources again. And Kotlin has a very elegant and simple way of using these auto-closable types in a safe way in a standard library. So this is a little bit similar to try with resources, only I prefer the Kotlin way because it deals with exceptions in the correct way. So we have this use function that we can call on any type that implements auto-closable or closable. Inside of the Lambda, we have then access to the myServer type. We can call the routes function. And if we run this main block, we can see that the server initializes, it handles a route, and it immediately closes, right? We see that the program exits with exit code 0. This is, of course, not what we want. We want the server to run for the entirety of our main process, right? Until we ask this main process to close. And what we can do to that is, we need to somehow wait or suspend. And since I love calling coroutines, I love suspend. I want to, of course, use this to keep the server running for as long as the main process is running. So I use the await cancellation function from the Kotlin Coroutines library. And what this function does is it suspends, and it waits until its outer scope closes. Right? Here, the outer scope is the run blocking function. Right? So our main thread is being blocked, and we are saying, okay, await the cancellation of our main thread, and when the main thread is asked to shut down, then also shut down the server. But when we run this piece of code, we see that something curious happens. You see, we initialize the server, we start handling requests, but when we send this SIGTERM event, we see that the close method is not called. Right? That's problematic. Like I said, we need to be careful with our resources. We need to do all the cleanup that we're supposed to do. We implemented auto-closable on our server. We're using the use function. We're doing everything that we're supposed to do, but the close method is not called. So before we go any further, what is this SIGTERM? So for those that are not familiar, there's, on the operating level, a couple of things which we call termination signals. And I'm sure everyone here has used them in some shape or form. So SIGTERM is what we saw in this example, and it's typically what's being used by technologies like Kubernetes or OpenShift to signal to a pod or a server that needs to gracefully shut down. So SIGTERM is a signal that can be sent to a process on our operating system to say, hey, please, process, can you shut down? Can you clear whatever you're doing so you're allowed to block this signal and do whatever resource cleanup and finalizing that you need to do, and then eventually you should shut down or close the process. One that I'm pretty sure everyone is familiar with is SIGINT, and maybe you have not used it directly. But for example, if you've ever pressed Control-C when you're running a Gradle task, you've actually sent a SIGINT event to Gradle to say, hey, Gradle, can you please stop what you're doing and stop your process, right? So if you've ever used Control-C in the terminal, then you've sent SIGINT events to processes. Similarly, if you've been running tests in IntelliJ, if you run the stop icon, or if you've been running application, if you press a stop icon, in IntelliJ also sends a SIGINT event to the process to say, hey, can you please stop what you're doing and shut down? SIGKILL is a little bit different than SIGTERM and SIGINT because SIGKILL is forcefully. So when you send a SIGKILL event to a process, you say, I'm not going to give you the time to gracefully shut down. I'm going to forcefully shut you down immediately. And maybe some of you, I've certainly done it a lot. If you've ever used a kill command in the terminal, for example, kill -9 Java, you can ask the operating system to kill all Java processes. You send SIGKILL events to all the Java processes on your machine. So most of us have used these signals in some shape or form. And in our previous example, no, I don't want to print anything. It's annoying. Why can I not? Yeah. Oh. This is very annoying. Nothing is working on my machine. Yeah, so I'm I'm going to force scale, and you see my shameful window with everything there. Right, so we saw that I forcefully killed Chrome. So we saw in this example, I was sending sick term to my main process, but it was not gracefully shutting down. So I demonstrated sick kill for you all. So before we go further, let's recap what is structured concurrency. So structured concurrency is a term and a technique that has been popularized by Kotlin and Kotlin X Coroutines. It's a technique that we've been using in functional programming for a very long time. And it's basically it's a mechanism or a technique to make sure that you're not leaking any processes. So imagine that we have some parent job process, and it can launch child process A, and it can launch a child process B, and in turn, child job A can launch 2 more child processes. When we consider the most parent job to be canceled, everything below needs to cancel as well. So before we can consider parent job to be terminated, all the child jobs also have to be terminated. So when we launch from the top to the bottom, and when we terminate, we have to terminate from the bottom to the top. And termination can be successful completion, right? So ideally, everything in our program runs fine, everything works as it should be, and we get successful completion, right? This is the happy path. But what we're actually talking about today is cancellation, right? We're canceling processes. So when parent job A needs to cancel, everything below needs to cancel, and it needs to cancel from the bottom to the top. Because when parent job asks child job A to cancel, child job A now has to cancel its children before it can be considered terminated or canceled, right? So everything works from the bottom to the top. And similarly, a third termination case is failure. When something goes wrong in child job A, then and it needs to terminate its children as well, or child job A cannot be considered terminated. So that is the pattern of structured concurrency in a nutshell. And how can we compare it to resource safety? Because resource safety actually has a similar problem or a similar technique that we can use to reason about it. So let's go back to our example. We have our main process that's running our server. And like I mentioned before, typically when we're building service, we need to work with a database. So the database can be considered the child resource of the main process. And alongside the database, we might have some metric registry that we use for analytics or logging to keep track. How is our server behaving? What is the performance of our service? And this, together with some other things, might form the dependency graph, right? So typically when we're writing servers, we have a bunch of dependencies that our server relies on or our service relies on. And these are typically, well, they're always childs of the main process, right? So we first start the main process, then we initialize the dependencies, and when all the dependencies are initialized, only then can we start the server. But oftentimes when we are writing microservices, the server, or the thing that is handling requests, is maybe not the only thing that we're doing on the microservice. Oftentimes we are maybe also processing some messages or some events in parallel to the server, for example, coming from Kafka or GCP PubSub, any kind of distributed message system or message queue or RabbitMQ. We need to process messages, store them in the database, then handle requests from the users. These are things that we're all doing in parallel, and typically it also relies on this dependency graph. So when we need to shut down the main process, we need to apply the same techniques as we've seen in structured concurrency. When we need to shut down the main process, we first need to shut down the server and the event processor before we can shut down our dependency graph. Because if we would shut down the database before we shut down the server, then some ongoing requests in the server might still require the database, and if it's already gone, then things will fail, right? So again, when we have these resources, we create them from the top to the bottom, and when we need to terminate them, we need to terminate them from the bottom back to the top. So how can we apply structured concurrencies for resources? Before we were using run blocking, and in the Arrow ecosystem, there is a new library called Suspend app that brings the structured concurrency pattern for resource safety, right? So we can reason about resource safety in this technique that we just discussed with structured concurrency for resources. And what is great about this library is multi-platform. So you can not only use it on a GVM, but you can also use it on macOS, Linux, Windows, Node.js, of course not in the browser or on Android because that would not make a lot of sense. So we love Kotlin, multi-platform, great. What is also interesting about this library is that it only depends on Kotlin X coroutines. So you can start using this library today without having to rely on any of the other things that you find in the Arrow organization. So we can now simply replace our run blocking from before with suspend app. And now, if you send a SIGTERM event to our main process or to our suspend app, you will see that the close method is now called. Great. Right? So we cancel, or we ask the main process to gracefully terminate. And we see that with the same piece of code, by using Kotlin Coroutines for await cancellation, we see now that the close method is called and everything gracefully shut down. Great. I mentioned suspend app is multi-platform, but auto-closable and closable is JVM specific, right? And we want to be able to write multi-platform applications. Ideally, this is what I love about Kotlin. I've recently been experimenting with Ktor on native, and the ecosystem is evolving quite quickly, which is super interesting. And we're on this advanced conference. So closable, it's missing Kotlin multi-platform support, too bad. But there's also a couple other things that I miss in closable and auto-closable from Java. It's a Java implementation. I'm looking for something that is Kotlin, it feels Kotlin. So I would also love to have suspend support, right? So the close method from Java is a regular method, does not have support for suspend. And typically when we're dealing with resources, often we need to communicate with the operating system when we're closing resources. Perhaps, for example, when you're processing messages from Kafka, maybe you need to send to your message broker a signal to say, hey, this was the last message that I processed. So there is some network communication that we might want to do when closing resources. So we would love to have support for suspend. And finally, since we're talking about structured concurrency, we talked about 3 different termination cases. There is no way to figure out in the close method from Java, are we closing because we canceled, or because our operation was completed, or because we failed? So I would also love to know that. And there is another type in ArrowFX coroutines, but we can imagine this simple type. So resource type, it defines a type A. You can say, okay, in a suspending way, I'm going to initialize my resource of type A, and then I add in association to it some release function, a finalizer that says, okay, for this type A, and its exit case, and its termination case, here is how I'm going to close and clean up my resource. An exit case is pretty simple. Like we mentioned before, it models the 3 termination cases: successful termination, cancellation, and failure. So we model it as a simple sealed class, right? The completion case, the cancellation case that gives you access to the underlying cancellation exception from Kotlin, and in the case that it failed, it gives you access to the underlying throwable. So how can we work and use with resources? Well, it very simply implements the same API as we saw before for closable in the standard library. It implements the use signature, but in this case, it does so by requiring suspend. Because this resource requires suspend, the use method also requires suspension. So how can we rewrite our original myServer stub to use this resource type? One thing that I didn't really mention before, what I don't like about auto-closable, it's an interface that you implement. So typically to construct the myServer, you call the regular constructor. But we are now using suspension, which gives us much more abilities. I want to leverage them. I made my constructor private. This is for 2 reasons. I don't want somebody to be able to construct my server without having the type save guarantee, with a compiled time save guarantee that the finalizer will be called. So by making the constructor private and providing a smart constructor that only returns the resource, I'm now guaranteed that if anybody tries to create my server instance, that he has to go through the use method, and therefore the finalizer will always be called. So the compiler will check for us that the finalizer is always called or the user is not able to use this type. And you can also see now that I renamed it to shutdown, because this is a method that we can now freely name because we don't have to implement an interface anymore. It has the ability to do suspension, and it has access to the exit case so that we can log or inspect why is our resource closing, why is it finalizing. And in this example, I'm using with context dispatchers IO. I'm just using it as an example. It could be any other suspending code that you might be able to imagine. But since we're talking about closing resources, I mentioned before, we typically have to do some IO, talk to the operating system. So typically we do that on the IO dispatcher. So to come back to our original example, not a lot of things changed. Instead of calling the regular constructor, I'm now calling this create smart constructor. I'm still using the use method as before. I'm still using suspend app. I'm still using await cancellation. And if we run this piece of code and we send the SIG term to the main process, we can now see that the server is also shutting down, but we were able to inspect why the server was shutting down. We can see that the server shut down because the termination case was cancellation. And it gives us access to the underlying cancellation exception that comes from the outer scope, in this case, suspend app. So I wanted to wrap up with a real-world example, and I already showed this real-world example, so let's take exactly that example to show. We want to implement a main method that has a dependency graph with a database and a metric registry, then we need to, based on that, launch a server. And in this example, to make it a bit shorter, I'm going to omit the event processor, but it will be quite easy to imagine how you could add that. So to create a database for a resource for a database, we can quite simply interact with Java. In this case, I'm using the Hikara data source, which is a very popular database pool library for Java. And because it implements auto-closable, we can quite easily lift the value into a resource. And what is funny here is I'm using Prometheus, which a lot of you will probably be familiar with. So Prometheus is a framework, a library to have logging on a centralized server. Here is for my metrics. And it's funny is we call the close method, but Prometheus does not implement closable or auto-closable from Java. So we are using the constructor that we saw before, and we have the acquire step, which initializes the Prometheus metric registry. And we have the finalizer, which calls the close method. And maybe also interesting to note is that this Prometheus registry is a top-level value. And the reason that it can be a top-level value is because the resource by itself doesn't do anything. Only when we call the use method on the resource will the acquire step actually run, initialize the Prometheus registry. We can then use the Prometheus registry, and at the end, when we are finished, it will call the close method. So these values are completely lazy, so it's safe to store them in top-level values. So how does our main method change? And for those that are familiar with Arrow, this might look a little bit familiar, but I will try to improve this pattern as much as possible. For those that were at Alejandro's talk before, we want to simplify things as much as possible. So let's do exactly that. But here in this first example, I'm opening a resource block, and inside this resource block, we get access to the bind method. And what the bind method does is it gives you access to the inner value of the resource on the left-hand side. And here, first we're binding the metric registry. We're then creating the database and binding the database resource, and that gives us access to the Prometheus registry in the database on the left-hand side. And what is interesting here is we are working with a first-in, last-out order. Like I mentioned, we create resources from the top to the bottom, and we close them from the bottom to the top. So first we create a metric registry, then the database. So when we close this resource, or this resulting resource, it first closes the database and then the metric registry. So from the top to the bottom, from the bottom to the top. And then we can also do the same to our server. So we create our server, we initialize it, and then in the use step we say await cancellation. So we're gonna use our resource of the server with the dependency graph until our process is canceled. But there's a lot of things that I don't like about the snippets. We see this bind method everywhere. It's quite obscuring. We have the use method at the bottom. It's might be quite foreign because we have this use method with only await cancellation on the inside. So to a lot of people that are not used to Arrow or this style of functional programming, this might look very foreign. There's a lot of overhead that obscures what we really want to do. And Kotlin is full of DSLs and a lot of power. And I was talking about structured concurrency, and in structured concurrency, we have the type coroutine scope that we use to launch and async values. And similarly, for resource, we can do something similar. So instead of having coroutine scope in the receiver of your extension function, we now have a resource scope in the receiver of our extension function. And inside of these functions, we now have access to a small DSL that we can use to work over resources. So in the first example, before we were using resource from autoclosable, and that was giving us a resource of a Hikaru data source in the return type. Here I'm calling a DSL function called autoclosable, and we are just seeing that we get Hikaru data source in the return type. There's no more wrapper. Since there's no more wrapper, there will be no more need to call bind. There will be no more need to compose these things in a complex way. And similarly for the metrics registry, which I now turned in a function because we're using suspension, because these are effectful things that we're doing. I can have an install function which has the same signature as our resource constructor. And in the first parameter, it takes a suspending function that creates the resource, in this case, the Prometheus registry. And in the second, or in the trailing lambda, we have the finalizer, where we say, okay, when you're finished using this resource, call the close method. And this is quite interesting because if you are familiar with calling coroutines, this might look very familiar. Instead of having coroutine scope in the receiver, we now have resource scope in the receiver, and it gives us access to a specialized DSL, and it evaporates or removes the need for wrappers in the return type. So if we now update our example, and I'm still using the resource block as before, we can see that all our bind methods have disappeared. Right? So a lot of the complexity that we had before for calling bind, this specialized API that we had to learn to create wrappers and then unwrap them, it has all disappeared. And there's still one thing that I don't like, and I mentioned it before, and we still have to call this use method. And I think we can still take this a step further, because I've already been comparing resource scope to coroutine scope, and there's another function in structured concurrency that we might be familiar with. So, similarly to the function coroutine scope, we can also have a function resource scope. And resource scopes works very similar to coroutine scope. Inside of the resource scope, we can call our functions that have resource scope in the receiver, like we have here. You can just call them, and the resources get created, and the lifecycle or the finalizers are guaranteed to be called when this block finishes. And here, so at the end of this block, there's no more need to call use. I can now simply call await cancellation. So this block, or this DSL block, works very similar to the coroutine scope block that we know from Kotlin coroutines. We have this resource scope function. We can call the resource DSL inside, and when this lambda block finishes, we are guaranteed that the finalizers are called from the bottom to the top. So now, when we ask this main process to be canceled with sig term, the await cancellation function will finish. The resource scope block will finish. We will see then that our server closes because that is the resource that we created the very last. Remember I said first in, last out. So first my server will close, then the database will close, and then the metric registry will close. We've now seen that we can apply the same principles as structured concurrency to reason about resources in a type-safe way. And you can find two production examples applying these patterns in real-world lifecycle examples. One is on the 47 degrees repository on GitHub, and it is actually implementing the exact example that I mentioned before, it is also communicating with Kafka. So it creates a data source, it creates Prometheus registry, it communicates with Kafka, it sets up Sacator server, and then the second one is on my personal GitHub, and there's a couple of sessions with JetBrains on YouTube that I talk about this example, and it applies the same patterns with Arrow, structured concurrency for resources to build microservices in type-safe ways. And I'm missing slides, but to make a small conclusion, structured concurrency is a pattern that we already know from Kotlin. So we want to be able to apply the same way of thinking for resources. And the resource data type from Arrow gives us exactly those powers. And the suspend app gives us the powers for thinking about resource safeties in terms of structured concurrency. So both these things together give us a very elegant way to, in a very Kotlin idiomatic way, think about resource safety and graceful shutdown without having to impose any strong learning curve or complexity in the code base. Thank you so much for your attention. I think there's still some time for questions.
Yes, I would say great applause for Simon for his talk.